Swayam Prabha. Digital India. Educated India.
So, today we are going to talk about a new data structure which is called range searching. So, before we move on to what is this data structure is, let us start with an example. So, suppose you have a data of a set of employees of certain organizations, say NICER, and you have two components of the data. One is the age of the employee and you have the salary of the employee. You have only two. For the timing, I assume that this is a database where you are storing these two information for all the employees. Now, what you want to do is to look for a set of employees whose salary and age belongs to a range. For example, here we are looking for set of all employees whose salary is between 20,000 and 30,000 and age is between 30 to 40. If you are familiar with database management system, this is kind of a very common example of a query. Usually the query ranges are much more, there can be much more dimension to each query, but for the simplicity let us assume that, let us start our discussion with the assumption that we have only queries in the two dimensional data set, right. So, our objective is how to report all the employees which can be modeled in a two dimensional points in a two dimensional plane very quickly, quote unquote very quickly. That we are given a set of points in a two dimensional space which is exactly the employees of the organization, and our objective is to, when a query rectangle comes, we have to report all the points which lies inside the query rectangle. This is a typical geometric problem, and the rectangles we will consider are axis parallel. Okay. How to do this? So, when you are having this kind of problems, can you give me a naive solution? Give me any solution that you have to design a data structure so that this can be achieved. Any solution. Much more trivial, forget about grid, much more trivial, which will definitely work. First thing, you have to make sure that your solution works. Very good idea, more trivial, more trivial. We will go into that details. Just store the points whenever a range comes. For each point, check whether that point is inside the range or outside the range. Definitely correct solution. First, we have to sure that whatever solution I propose is correct. How much time it will take to build the data structure? N or the input data set itself is a data structure. How much time it will take to report a query? N time, right. So, our objective is, but you can understand that the data structure that we will build only once, and maybe infrequently we will make some changes to the data structure. But these queries will come much more often. For example, if you look at Google, how many pages, new pages it indexes every day? That number is quite small compared to the number of Google searches we have daily. So, query number of times a query comes is much more frequent than number of changes in the data structure. So, ideally what is our objective is to, we will not hesitate to pay a little bit more to construct the data structure, but we would like to reduce the query time. So, there are two aspects. One is pre-processing time, or in other words what is the time needed to build the data structure. Second is the query time, and the third is the space the data structure takes. That is also important, because if you are storing the data structure in your computer in a small data structure, it does not matter. But if it is a huge data you have to store, n square and n log n creates a huge difference. So, the three aspects: pre-processing time, data structure size, and query time. Clear? Okay, very nice. So, you have attended few of my courses. You know, when we are not able to solve a problem, what we do? We reduce its complexity. So, let us do the same thing. We started with a problem that we want to, given a range, we want to find out what are the points inside in 2D, but it seems too difficult to me. So, I will try to solve this problem in 1D. What is the equivalent problem in 1D is that you have a set of points on a line, you have to pre-process them, so that whenever there is a query rectangle comes, query interval comes, you have to report all the points inside very quickly. Now, again you have seen in my previous class that if you have to report n points, you have to spend n time. So, what we are looking here is a output sensitive algorithm. That means, we are looking for some query time plus k, where k is the output size. Clear? How to solve this? So, the first trivial solution that comes to my mind is similar to what you have suggested. I will just sort the points and store them. Just sort the points and store them, right? How will report a query? What is a query? Query is two values a and b. Do you need to do both? I am not interested in number of, I want to report all the points. So, I will only search for, yes, yes. So, you are perfectly correct that if you want to report the points, then what I will do, I will search for, if our range comes like x, y, I will search for the x in the sorted sequence and start reporting until I reach y. Log n for the searching, reporting is k. Simple. Any doubt till now? Okay. So, he has raised, one of your friends has raised a very fair question, that, or very fair aspect of the same question, that say I do not have to report the points, I am only interested in reporting the number of points that are inside. That is another query, that let me know how many employees have salary between 20,000 and 30,000 and age between 30 and 40. I do not want the name of the employees, I only want to know the number. So, previously our argument is that I need something like a log n plus k, because to report k numbers I have to spend k amount of time. But when I reverse or change the question slightly, that I do not have to report the name of the employee, I just want the count, then can we solve this query in log n time? Can we? This is also a solution proposed by him, that you do a binary search on x, you do a binary search on y, when the range is x to y, you find the difference between their indexes and report that. Just sorted sequence.
So yes, we could, if we have a prefix then we have A and B. So like the number of points until A, then number of points until B, and subtract them, and then we will get a result.
Yes, that's what. That's what. Okay. So we can do some kind of we can have a solution. We are fairly have a simple solution for 1D problem. But in the next few slides, I will give you a little bit more complicated solution to this problem. Why? Because it will help me build a data structure for the 2D problem. Clear? So, what is my solution? It is the same solution at sorting all the points. So, what I will do, suppose this is my points. What are my points? Is 5, 10, 22, 28, 34, 36, 50, 55, 62 till 90. So, this is my given set of points, and I am looking for a range or query, suppose 34 to 80. What I will do, I will create a balanced binary search tree. The way we have created it earlier, it is the same way we will create a balanced binary search tree. And what each internal node represents in this balanced binary search tree? It represents an interval. So, how I am creating the balanced binary search tree? This interval, this node represent the interval 5 to 10. 22 represent the interval 22 to 38. 65 represents the interval 50 to 90. Leaf nodes are intervals of where it contains only one point, and any internal node is the union of its left child to its right child. 36 is the interval from 34 to 40. No, what 34 represents? This, right, and I will extend with this 40, so it will become 34 to 40. Why? Yes, of course, we have duplicate nodes. So, okay. So, this is the balanced binary search tree, where the leaf nodes are the given points from the bottom to top. What are the values stored in the left subtree of 36? All the values less than 36. So, what are the values less than 36? Less than equals to. Okay? I am taking the highest value, largest value from the left subtree, and I am putting it in the value of the node. So, what is the highest value here? Is 65. I am storing it here. what is the size of this data structure? Hmm? 2 to the power n. Very good. What is that? Hmm? What is a balanced binary tree with n leaf or have number of, what is the number of internal nodes?
Less than 1 if the number of leaf is L and the number of internal nodes would be L minus 1.
Hmm? What is the sum of n by 2 plus n by 4 plus n by 8? So, all together order n, right? This all together takes order n space. Doubts? It is GP series. Okay. So, we have this data structure. Now, the question is, we have built a data structure, but we need to do a query on this data structure. How to search for a range? What is our range? Is 34 to 80. How to search for a range 34 to 80? I want a runtime log n plus k. I want to report all the points which is inside 34 to 80 in time log n plus k.
Search for 34 and 80 and then report all.
Very good. We will search for 34. This is the search for 34. Right, when I am going left, what I can say, if I move left, whatever is in right, if the search path goes left, whatever in right is in the range. I look for 80 similarly, and I will report the nodes. Now, depending on the search path, I would like to divide the nodes of the tree into two parts. Into three categories. One is a white node, the nodes which I will not traverse. Then I will have gray nodes. Gray nodes are those, suppose each node we have seen represents an interval. If the interval is partial inside the query range, we will call it a gray node. For example, if you see this is the range for 36. This is the interval associated with 36. What is my query? Query is 36 to 34 to 80. So, 34 to, yeah, there must be a mistake, it should be 36 to 80. So, this 36 to 80 is not completely inside the interval associated with 36. So, 36 becomes a gray node. I am not sure whether I have to report all the points inside or not. What is a black node? For which I am sure that this is completely inside. For example, along in the range of 50, the interval associated with 55 is completely inside the query range. So, the node 55 will become black node. So, you have black, gray and white. Is it clear how we are naming the intervals? White is, I will not even go into that part, for example 10, right, because when I know that 34 comes this way, so 10 is outside the range. I will not visit any of these nodes. So, these nodes remains white. The nodes for which I am not sure whether, or the whole node will not be reported, that I am calling gray, but partially the node will be, the subtree will be subtree rooted at that node, and the black nodes are those which will be completely reported, right. So, how my search algorithm will work? First I will find a split node. What is a split node? Split node is from where the left value and the right value splits into two different subtrees. Here in the previous example, split node was 40, but here when I am looking for 50 to 70, 65 becomes my split node. From 65, the left search will take one path and the right search will take another path. In other words, this is the first node while searching for the root is in between the range given to me. What is the range? 50 to 40, 50 to 70. 40 is between 50 to 70? No, it is outside, so it can't be a split node. But 40 is less than this node, less than this range. So, which way I will go? I will go to the right. Does 65 is in between 50 and 70? Yes. So, that is my split node. Right. Now, from the split node, I will start my journey and I will move left first, then I will move right. Right. Now, when moving left, what I know? That if you moving left of a child, so I will start with here 55, next I go to 50, from 55 to 50 I am moving left, so I have to report all these nodes. So, this all becomes black nodes, right. 55 becomes black node. Similarly, here 70 I am moving on the, if I have to move right, suppose the search path is something like this, then 70 would have become a black node. Okay, very nice. So, this is the algorithm, the overview of the algorithm, that when we start, first I find the split node, that is the first thing I would like to do. Then depending on the split node, if I go left, I report the whole subtree in the right, or if I am moving right, I do not do anything, I just keep moving on the right. And you have to similarly do this for the right extreme of the range tree. Now, the obvious question, what is the runtime of this query algorithm? What is the runtime? Okay. very good. Size is 2 log n, but incomplete, plus k. So, systematically if I have to count this, what I am doing? White node I do not count. What is the number of grey nodes that I will visit? 2 log n. And what is the number of black nodes? I do not care, I will be charge this on the output size, because I know that whenever I have to go left or this, I will do not mind, because I have to report the whole subtree, and that is on the output size. I will charge that on the output size. Clear till now? Now what about range reporting? Can I do it in log n time? This is, sorry, range searching, range, not range reporting, range counting, but I have to count the number of points inside the range. Instead of reporting the points in the range, I have to just report the count, how many points are inside the range. Can I do it in log n time? Yes, please raise your hand, and what is your answer? You? Yes. For each node, what is the suggestion is that for each node I can store the number of leaf nodes below this node. So, what I will do, when I am going left or while coming back, I can just add this number. So, this is 1, this is 1, 2, 3, 4. So, while coming back, I just add 4 with the whatever number I came from here. I will not go inside this range. So, everything can be done in log n time. So, this is a short story I am telling in a long way, but let us see why this is going to help us in the 2-dimensional case. But this is clear, please raise your hand if it is not clear. I will explain once again if it is not clear. Please raise your hand. If you are not able to understand the 1-dimensional query, not be able to understand 2-dimensional case. Yes, sir. Clear, it will be clear. Just wait. But this serves our purpose. We can search in log n time. Data structure size is order n. We are good, right? That's what same thing we can achieve by a simple sorted list, right? But if you think for a time, suppose you have a sorted list. Can you insert or delete infrequently, but still there is a chance that database will be updated? Suppose you maintain a sorted list, how can you insert or delete in how much time it will take? But here, so this is one, but there can be many easier solutions even supporting log n time, but this is. So, what we are doing? We are allowing updates in log n time, updates in the database log n time, query log n time, storage order n. So, it seems like a decent data, fairly decent data structure. Right? Is it clear? So, exactly what I will do is, you go to this, the range is 50 to 70. What is the root node? 40. 40 is left to the range. I know that all the values greater than 40 is stored in the right subtree. So, I do not need to search in the left subtree, I will go right. What is the next node? Next node 65. That is in between the range. So, this is my split node, because I know that this is 65, that means left subtree contains values which are less than 65 and right subtree contains values which are greater than 65, and my range is like in both the trees, like expands in both the direction. So, I have to search for both the trees, both the subtree rooted at 65. That is why 65 becomes a split node. Even for like 64 to 70, if I have my query range 64 to 70, I have to still 65 becomes my split node, because the query expands in both ways from 65, because I do not know at standing at 65, I do not know that whether 64 is inside or not, right. Clear how I am finding the split node? 34 to 80, yeah, 34 to, yes. So, 34 to 40 is in between. So, the root node is my split node. Yes, this is how I am building. How I am building? I am creating a leaf nodes and then pushing. I am looking at the highest value present in the left subtree. I am pushing it here. That is how we build a balanced binary search. This is exactly how we build a BST. Okay? All good? So, this is we are done, this is done. So, this is the final theorem that we can do everything in log n time and construction order n time. Say n log n time to construct, storage is order n, and log n time for update, delete or query, that we are still in 1D. Then I can search, then we can sort in log n time, n time. Yeah, if it is queries are in the sorted order, only then it is possible. The points are in sorted order given to you. Otherwise, by building a balanced search tree in order n time, you will eventually do a sorting in. Yes. Okay. Yes. The question is, we have an idea. Let us see whether it is a good idea or not. When it is a good idea, when you can extend it to higher dimensions. Can we extend this idea to higher dimensions? Of course, yes. This is the basic of two range searching trees. One is this KD tree that I am going to teach you now. In the next class, Arijitda will talk about range trees, which is also generalization of this one dimensional range tree. What is the idea for KD trees? The same what we are doing here is we are dividing the points from the half and half in one dimension. Left I am pushing in the left tree, right I am pushing to the right subtree. This is the idea of constructing a one dimensional range tree. We will extend this idea. What I will do? What is given to me is a set of points in 2D. I have certain x coordinates and I have the y coordinates of these points. First, I will divide the points. I will find the median x coordinate and divide into two parts. Then in this division, I will find the median y coordinate of the left side and median y coordinate of the right side, and I will continue. So, suppose these are my points. What is L1 is the median left coordinate of the all the points given, median x coordinate of all the points given, and what L1 this node represents is the whole rectangle. This is suppose some arbitrary rectangle that I am drawn, which encloses all the points. Then what I will do? I will find the median y coordinate of the left side of the points. This is L2. This will divide the points into two parts, the points which are above L2, points which are below L2. Right hand side, I will find the median y coordinate, that will divide the points into almost two equal parts. right. These are the points, some points are above L3 and some points are below L3, two parts, the points which are below L3, the points which are above L3. Are you with me? Simple construction, and I will continue doing the same thing. Then I will find L4, first x, then y, then x, then y.
No always X, no always Y.
Hmm?
X followed by Y every time.
Yeah, every time. This is the scheme. This is a median x coordinate, median y, median x, median x, median x, median x, and continue like this. You have a question? Yes. Oh, what I am doing I should explain? Okay. First, this is a arbitrary enclosing rectangle of all the given points. I will divide them by the median y x coordinate. What is the median x coordinate of all these points? Is passing through P5. See that there are equal number of points left, there is equal number of points right. So one difference can be there, is median. You can choose one of them. There are two medians, you can choose arbitrarily one of them. Yes, of course. Otherwise, I will not get a balanced tree, so I cannot claim that this is a log n time. Because you give me any points, there exists any set of into half and half, almost half and half. Only can be one difference, right? Then I will split according to the. I will look at the points which are left to this line. Among them, I will find the median coordinate. Either I can choose this line L2 or I could have chosen this line. Both of them are median lines.
But here you see, when I draw that horizontal line, that L2 would be 2, so that side we have got 1 point here, 2. Only difference will be
Always 1. This is a property of the median. If the number of points is even, we have 2 median values. If the number of points is odd, I have 1 median value. Similarly, I am doing for the right hand side. I am dividing into 2 equal parts, the points in the right hand side of L1 into 2 equal parts, and that line is L3. First x, then y, now x. Half, 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 half. I will continue till there is only one point in each subdivision. Yes.
Why would they just center of find the center point,
Mm-hmm.
and then divide it into 4 parts, and then take its center point and then divide it into 4 parts, and by each node.
What do you mean by center point? Does a center point always exist that splits the points into 4 equal parts?
No, just not 4 equal parts, but
So these are my points, say n by 2, n by 2. How you will split?
just the point center.
What do you mean by point center?
Not exactly center, like median.
You are understand what I am trying to get here. You cannot find a center here. It is not possible. This is the example. The n by 2 points here, n by 2 points here. But you can always find the median in a one dimensional data.
it will be always a balanced tree.
Median in 2 dimensions.
Yes.
A point that is median of 2 dimensions data.
Does there such a point exist? There is something called a 2-dimensional median, but it is something completely different. You cannot define what you cannot define. There is a 2-dimensional median, but its definition is it's not going to serve our purpose. What is the median of 2 dimension? You find out any line through that point, it will contain at least n by 3 points. That is the definition of a median in 2-dimensional data set, not the usual notation of 1-dimensional median.
Or a point that is closest from the center of.
There is no center. How can you define a center? Look, this is hunches, right? It's good that you are like providing some hunches, that means you are trying to think. That is good, I appreciate. But you have to define it properly, what you want. So, but how that will divide the points, that I have no clue. Suppose this is the minimum enclosing circle. Suppose all the points are here. That's will lose the purpose. It's unbalanced, right? So you have to keep in mind, we want to create a balanced tree, otherwise this log n factor we never can able to guarantee. Otherwise I could have divided anyway, right? The thing that I have to keep in mind, that I have to create a balanced binary search tree, otherwise log n factor I cannot achieve. But still, let us see whether I can achieve log n factor or not. Let us see. So this is a overview of the algorithm to how to build the KD tree. I will find the median x coordinate, divide into 2 and recursively build the KD tree for 2 set of points. Clear? Are you with me? How much time it will take to build? Why? Why? N square n log n, n square log n. Yes. So when you are not sure about something, write down the recurrence. What we are doing? This is a recursive algorithm. Finding the x median or y median, divided into 2 parts, build the 2 trees recursively. How much time to find a median? Order n. Divides into 2 parts, n by 2, n by 2, yes.
Are the points sorted? If they are sorted, then median is constant.
No. Initially the set of points are sorted, right? X axis, y axis. Does the point sorted here? You have a sorting of all the points. Do you have a sorting of all these points here? You have to find a median for these points as well.
So we don't have to sort again and again, like we just pick those points which are already sorted.
Yes, but you have to at least divide the points into 2 parts, right? That will take n time.
Yeah, the complexity is due to picking those choices.
Yes. So anyway, I cannot avoid order n. You can do some tricks, but I cannot avoid order n. So what are the recurrences? Tn equals to 2 Tn by 2 plus order n, which is n log n time.
So what is why is it called KD tree? KD means what?
K dimensional tree. We'll see. D is the dimension. The easy part is over. How to search for a query rectangle? How to search for a query rectangle? Still easy. Don't be afraid. What is L1? Is the whole square. Right? I am seeing that L1 is a line. Does the query rectangle participate in both the sides of the L1? L1 is a line. Does the query rectangle, this is my query rectangle, participates, the query rectangle is the blue one. Does the query rectangle participates in both the sides of L1? Then L1 becomes my, very good, my split node. Right? I go to L2. Yes. In L2, I have this is my line L2. Does my query rectangle participate in both the sides of L2? Right? So what I will do? I will go only to the left, only one side. right. From L2 I will not search this part, this nodes becomes white, but I am not sure whether it contains all of this what is below L2 or not, contains all the points is below L2 or not. Certainly not, do not cover the whole rectangle that is represented by this L4 vertex. So, it becomes a grey node. I am not sure what to report, what not to report. Similarly, I go to right side rectangle becomes this. Does it participates in both the sides? Yes, then I will search in both the direction. I will go left, I see when I go, this is P6, 6P7, oh this is below this line, left hand side is below this line, right, and I will continue like this. Is it clear till now? P6, okay. So, we have L6, L6 is which one? Yeah, this is L6, right. I divide L6, this L9, yeah, L9 should be grey, L9 should be grey, it is a mistake, L9 is grey. Then I go to P6, what is, this is my L9, right, L9 divides this box this is the box for L9. Right, then okay, sorry, my mistake. So, this is L9. So, this is L9. L9 divides the query into two parts. You see that above in the right hand side of L9, this is the rectangle. This is completely inside the query range. That is why this is black. But the query, the rectangle below N line, is it completely inside the query range? No. That is why this is grey. So, associated with each vertex there is a query rectangle. If that query rectangle is completely inside the search query, then it becomes black. If it is completely outside, then it becomes white. If the query rectangle intersects the rectangle associated with the vertex, it becomes grey. Is it clear? There can be three cases. Each vertex there exists a rectangle associated with it. If the query intersects that rectangle, it becomes intersects, not contains. Intersects, then grey. Contains black. Do not contain, do not intersect, do not contain white. Three cases. Clear? It is very important. Are you with me till now? Very nice. This is the gist of the query that we are doing. P3 is this node, na? Does the query rectangle contains this node? No, it intersects, but do not contains. Yes. 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 Gray nodes will go inside. Yes. If it is so, at each node I will store the range and I can store the points as well. It will not affect my complexity. That is below. If I see the range is completely inside, that the query range that I am looking for contains the range associated with the vertex, I will just report all the points, and that is on the size of the output, that I will charge on the size of the output. What I am saying is that with this node there is a rectangle associated and I have a query rectangle. This is query rectangle, this is the rectangle associated with this node. What I will do? I will go inside, I will check whether, first thing I will check is whether this query rectangle even intersects this rectangle stored at this node or not. If this do not intersect, I will do nothing, it becomes white node. If it intersects, I will see that whether it contains the whole rectangle associated with this or not. Then it becomes black. I do not have to go inside further. I will just report the point stored, or I will forward the count to the higher dimension. Right? If it intersects, if it partially intersects, it becomes grey. I will check whether it intersects my left part or right part or not. If it intersects both the parts, I will forward the query in both the directions. If it intersects one, I will forward this to only one. Right? White node, query rectangle do not intersect the region associated with that. Grey node intersect but do not contain. Black node completely contains. Complexity, we will see how to calculate. Two things we are sure, we do not have to count the white nodes, because we never visit the white nodes. We do not have to count the black nodes, because I am reporting everything inside black. So, that will be charged from the like previous case, that will be on the output size. My only concern while finding out the query time is that how many grey nodes I traverse, because it is not a straight line log n size path. Previously in one dimensional case, what we have is a straight line, something like this, and it is 2 log n, straightforward. But it is arbitrarily I am doing. I do not know, if I go left, then I have to report everything. Look at this, here I am going left, but I am not reporting everything here. So, I do not know which way I will go. Is the problem clear? I am good with black, good with white. How to count the grey nodes? To count the grey nodes, I will use a small trick. What is the trick? The trick that I am keep repeating many times. What is a grey node? Grey nodes are those nodes which are partially inside the query rectangle, right? Right? Are you with me? Very good. Look at the nodes in the leaf level. Suppose this is the nodes in the leaf level. Which boxes they represent? They represent the boxes in the, these boxes they represent, right? In finer subdivisions they represent, the last subdivision they represent, right? Are you with me? So, we have 4 lines. This red box are the last, you go to the last level of decomposition, the final elementary boxes that you get, that is represented by the leaf nodes. What is this leaf node? This node. This is the union of these two boxes. So, then maybe this and this, maybe, say. Right? Now, tell me how many boxes from this elementary boxes at the lowest level, how many boxes a query rectangle can partially intersect? Total number, what is the total number of boxes? N. What is each side of boxes? Root n. If you have a grid of size n, there are n boxes in the grid. What is the size of the each size? Root n. If you draw a straight line, how many boxes you can intersect? Order root n always, right? 4. How many? 4 root n. So, let us say I am counting only one line, say it is root n. Are you with me? How many boxes this line, only this line intersects? How many boxes means how many boxes from this set of boxes? This line intersects root n. Go one level higher. How many boxes it intersects? Root n by 2. Eventually, how many boxes it intersects? What is the query complexity? So, we have started with the objective to achieve log n, we could not, but we at least settled for something better than linear. Log n we could not achieve, not able to achieve log n, but whatever we have achieved is better than linear time. Yes, sir. You have a root n cross root n grid. Think of this grid as something like this. If I draw a straight line, how many lines I can intersect? Root n, right? That is what I am doing here. Only think about this line, forget about 4. This is whatever number I will get, I will multiply with 4. What is our objective? How many boxes these 4 lines intersect? I will count for only one line and multiply that count with 4, because we are in computer science domain, we do not care about constants, right. I am just interested in finding how many boxes this one line intersects. To do that, I am looking for the how many boxes from the last level this line intersects, that is root n. Next level root n by 2, next level root n by 4, like this. So, eventually if I sum them up, I am intersecting at most order root n many boxes. So, how many time I am spending in query? Root n plus k, k is the black nodes, right. Now, comes back to his question, why KD tree? It can be very easily generalized for any dimension. What I will do? X axis, suppose 3 dimension x axis median, y axis median, z axis median, then x axis median, do the same thing. Yes, of course. This will be the query complexity, which is almost, if the D increases, this is almost like a linear. We have achieved, we are able to create a data structure which works very well for small dimensions. Still we have to do something which works well for the higher dimension. That will be done in the next class. That can we achieve log n for 2-dimensional queries, 2-dimensional range queries. Okay? Yes. Because like how many boxes you will intersect, how many lines you have in a query, and then you have plane, 3-dimensional plane, how many boxes you intersect. This comes from the counting of the gray nodes. Then we will see that how this comes. Okay? Okay, thank you.